All right, welcome everybody. We are pleased to have Dylan Temples as our NPA speaker today. Dylan joined Fermilab as a Letterman Fellow in 2021 after receiving his PhD from Northwestern University, where he worked with Professor Eric Dahl on the Lux-Zeppelin experiment. At Fermilab, his research is centered upon developing quantum sensors for direct detection of dark matter. And Dylan splits his time between the MAGES. Is it MAGES?
There's an internal disagreement, but I say MAGES.
MAGES 100 atom interferometry experiment and efforts within the Quantum Science Center to develop dark matter detectors leveraging superconducting devices, including qubits and MKIDs. So thanks. Please take it away, Dylan.
Excellent. Yeah, thanks for the invitation to come and speak on this beautiful fall day. It's a little bit nicer here than it is in Chicago, though we're still not quite in winter yet. Right, so I'll talk about some of the work that I've been doing at NEXUS. I'm developing kinetic inductance Phonon-Mediated detectors to look for dark matter. So just a brief outline, I'll very quickly go over dark matter direct detection, then give an overview of what these kinetic inductance Phonon-Mediated detectors are, talk about a energy resolution measurement that we did at NEXUS, as well as some pulse shape modeling. And then if there's time, which there's probably not going to be, but I'll talk about some detector optimization for dark matter, as well as some new efforts we're thinking about for both dark matter and quantum information science. So there's a lot of dark matter in the universe, 27%, of course. And we have evidence for the existence of dark matter, ranging from scales at scales of galaxies, up through galaxy clusters, up through the large-scale structure of the universe, and the cosmic microwave background. However, while we have all this evidence for it, our knowledge of what this dark matter is or the ignorance thereof is remarkable, according to the European Strategy for Particle Physics. So some of the things we don't know is what is the particle's mass. If dark matter is a new particle, it can span basically 50 orders of magnitude from the limit where you can't have an elementary particle heavier than about 10 to the 28 eV. And if you're lower than about 10 to the minus 22 eV, you can't fit dark matter inside of a dwarf galaxy. So that kind of bounds it. And of course, this is a simplified view of all of the classes of models that would populate this thermometer of dark matter mass. I'm going to be focusing kind of in this region here, the light dark matter. And we also don't know if the dark matter interacts with the standard model beyond just gravity. We hope it does, because we keep building dark matter direct detection experiments that look for these particle physics interactions. And so here we are in some spiral arm of the Milky Way galaxy. And as we orbit around the center of the galaxy, we move through this dark matter halo here. And we trail behind the constellation Cygnus. So from our point of view, it looks like the dark matter wind is coming from Cygnus. So that comes to Earth, and we build detectors here, usually underground for background mitigation reasons, and then hope that that dark matter comes in, interacts with our bucket of material or a detector, and produces some measurable signal, whether it's photons, charge, or light. And this is for the particle dark matter case. Things are different, of course, if you're looking for axions or ultralight dark matter. And through these, with these detectors and these signals, you can look for a number of different interactions between the dark matter and the standard model. We've done a great job at looking for dark matter, especially nuclear recoil dark matter, above about a GeV. But there's a lot of wide open parameter space to the left and down on these plots. And so it is interesting to start exploring this region. There are still well-motivated models of dark matter in these unexplored parameter spaces, but it's challenging to look for dark matter that is this light. And it is challenging because the energy that is deposited in your detector is about 6 orders of magnitude lower than the dark matter mass for a well-matched target for your dark matter mass. And that means if you're looking for an meV-scale dark matter mass, you have to be sensitive to EV-scale energies. Forward here. So, right, 1 meV, if we're at 1 meV, our maximum energy is just over an EV, and the mean energy carried by the dark matter is below an EV. And so if you want to look for dark matter in this mass range, you have to be sensitive to sub-EV quanta, ideally sub-milli-electron volt quanta. And so, as I mentioned, we'll be focusing on this kind of light dark matter region between a few hundreds of MeV down to a few hundreds of keV. And one of the technologies that we can use to look for these sub-eV quanta are kinetic inductance detectors. So if you cross out the phonon-mediated here, I'll be talking about kinetic inductance detectors. These things have been used for photon detection for things like focal planes of telescopes and whatnot. But we are looking not for direct impacts in the superconductor, which I'll talk about in a second, but rather phonon-mediated signals from interactions in the substrate. And so here you've got some dark matter coming in. It scatters in your substrate, usually silicon, but we can go beyond silicon. And that will produce some photons in your substrate that rattle around until they hit a superconducting thin film, where they will break the Cooper pairs that carry the supercurrent into quasiparticles. And so the energies needed to bind these Cooper pairs are very low. And so if you are sensitive to a very low number of quasiparticles, you can in principle be sensitive to very, very small energy depositions. So we're talking, these are hundreds to tens of micro EV at a 10 millikelvin temperature. This class of superconducting thin film phonon sensors includes things like transition edge sensors, microwave kinetic inductance detectors, which I'll be talking about, superconducting qubits, and more. So what is a kinetic inductance detector? It is some LC circuit that is patterned into a superconducting film, and you probe the properties of this circuit by measuring the complex transmission for the forward scattering parameter S21. This is an LC circuit. The inductance from this circuit comes there's a geometrical inductance that you get. There's also a inductance that you get from the inertia of the Cooper pairs. These things are relatively massive, and so if you apply oscillating voltage to a chunk of superconductor with kinetic inductance, the current will lag behind the voltage because of the inertia, and that is just an inductance. And so in principle, if something comes in and breaks the Cooper pairs in your superconductor, whether it's incident photons or phonons, that starts to break Cooper pairs. That produces an increased quasiparticle density, which then modulates the inductance of your circuit, changing your resonant frequency to lower values and changing the quality factor of this resonance. So it's width and amplitude here to lower values. And so in some standard state, some quiescent state, you might see something that looks like this, where you're measuring the magnitude of your transmission, this S21 parameter versus frequency. But when you absorb phonons or something, photons even, this will move to the left and it will get shorter and wider. If you look at this in complex space, you can break this down into movement in the frequency direction and movement in the dissipation direction. So this is basically the imaginary axis of the S21 parameter and the real axis here. This is some idealized version of that. Good. So a kinetic inductance phonon-mediated detector, in contrast, is to a regular kinetic inductance detector, looks for these athermal phonons that propagate in the substrate until they are absorbed by either a sensitive piece of superconductor or some insensitive piece of superconductor like your feed line or some other mounting structures. This is one of the devices that we work with. This is not the device that I'll be talking about for most of this talk. These things are attractive for dark matter searches for various reasons, or as detectors for various reasons. They are natively frequency domain, so you can multiplex these things relatively easily and scale up to, yes, question.
Just on the last slide when you're talking about NPAs. So when a Cooper pair is broken into two quasiparticles, do those two quasiparticles lose some of their inertia, like during that process?
Yes, so their effective mass is lower than the Cooper pair mass, so you have lower inertia.
Okay.
Great. So in addition to being frequency multiplexable, they are non-dissipative, so you can use QIS techniques like parametric amplification. And this architecture provides two advantages for particle detection. One is a path towards sub-eV energy resolution, which, if you haven't figured out, this is what I'm going to be talking about so far, as well as a pixelized photon readout. And so for moving towards sub-eV energy resolution, we have direct sensitivity to pair breaking phonons. We don't have to worry about shuttling quasiparticles around, though you can potentially get gains if you use quasi-particle tracking to bring signal from other pieces of metal into your inductor. At the state of the art right now, the energy resolution of these things is about 30 eV, where if we compare that to a phonon coupled TES, this is about 700 milli-electron volts from a result that came out earlier this year. If we are able to push to sub-eV energy resolution, we would have sensitivity to sub-GeV dark matter masses, both nuclear recoil and electron recoil signals, as well as sensitivity to the PP solar neutrinos. Additionally, we can, as I mentioned, multiplex these things, which would allow us to deploy large arrays with the same electronics on the warm side as needed to read out just a single resonator. And you could do things like reducialization and reject surface events, which can be a background, especially in a detector like this, where your detector is basically all surface. All right, so how do you read these things out? This is, question.
So from Phonon's perspective, how transparent the interface is? So you need to kind of go into the aluminum to break the Cooper pair, right?
Yeah, that's right.
And how transparent that process is?
So we don't have a concrete number on the absorption probability of the phonons into the thin film, at least not off the top of my head. Part of this measurement is measuring our ability to collect phonons. So I will talk about the measurement of what we call eta phonon, which is the efficiency for collecting these phonons. That folds in the effects of like probability of actually absorbing a phonon from the substrate into the superconductor, as well as general phonon loss. So it's kind of lumped in the view that we're looking at here.
And just one quick more question. Is there any way to distinguish where phonon is generated?
In a device like this, not really, because you have a single readout point. But if you had a device more like this, where you have multiple resonators, you can do position
No, I
reconstruction.
meant more like a silicon convergence element.
Oh, yes. And you can do that by the phonon rise time. So if you have a direct impact onto the superconductor, you get a rise time that is set by the ring up time of your resonator. Whereas if you have a phonon signal, that takes some time to propagate to reach its maximum amplitude. And I'll talk a little bit about that.
Thank you.
Yeah. Okay, great. So how do we read these things out? So this is a frequency scan. So transmission, magnitude of transmission versus frequency. At some quiescent state, we might be in this blue region. So we tune our radio to our 4.242 gigahertz. This is the resonator that I'll be talking about for this talk. And then you move to a time domain measurement. So at the resonant frequency, you're measuring some flat transmission in time plus noise, and noise is very important. I'll be talking about that. At something happens, in our case, incident phonons, those will hit the kinetic inductance detector, giving you a prompt increase in your quasi-particle density, which shifts your frequency and quality to lower values. So you kind of map this trajectory going from blue to red here. This is exaggerated because this is a temperature sweep. The same idea holds for phonons. Yes?
Are these gigahertz phonons that are?
Yeah. They would be... So the frequency of the resonator does not care about the frequency of the phonons, provided that they have enough energy to break Cooper pairs. So I think of them in EV, but of course there's a frequency translation there, giving some dispersion, but I don't have that ingrained in my memory. I don't think about them in frequency, but good question.
For aluminum, it would be 90 gigahertz.
Great. So yeah. Okay, right. So as you break these Cooper pairs, you increase the density, you get a sharp jump in the transmission at your resonant frequency, right? So if I was reading here and the blue line shifted to that red line, now instead of reading minus 16.5, I'm reading minus 13. So you get a sharp rise. The quasi-particles will recombine into Cooper pairs given their lifetime in the superconductor. And so your resonance feature will slowly return to its quiescent point. So in the time domain, that looks like a pulse, and that's how we can use these. So if you're a HEP person, you think about pulses, and once you start seeing pulses, you go, okay, I've got a detector. And we can break this down into the two readout quadratures that I had mentioned before. the frequency quadrature, which is in some way related to the phase of the complex number, and the dissipation direction, which is in some way related to the amplitude of the S21 parameter. There's some mixing between these. So I mentioned noise was important. There are three main sources of noise in these detectors. We have thermal noise from our first stage amplifier. This is white in both quadratures. We also get noise from electrically active two-level systems that has a characteristic 1/√F shape in the PSD, the power spectral density. And I'll show some of that later. But interestingly, this only affects the frequency quadrature, not the dissipation quadrature. But I should point out, we'll get there for a second. And then there's generation recombination noise. Again, affecting both quadratures, and this is white up to the roll-off at the quasiparticle lifetime. And this comes from just Poissonian breaking and recombining of Cooper pairs due to thermal energy. These, while they have different frequency dependencies, they also have a different power dependence, and so we can use that to identify various sources of noise. And this generation recombination noise is basically your fundamental limit, but it's temperature dependent. So the colder you go, the more you suppress this GR noise. And so just to illustrate how noise is important here, so if I have a very noisy time stream like this orange waveform versus this blue waveform, it obviously is going to be much easier to observe a small pulse if my baseline looks like the blue one versus the orange one. All right. So now we're going to go back in time to the prototype device at Caltech from 2012. This was Dave Moore's thesis. The energy resolution of a KIPM device or KIPM detector with some number of resonators on it is related in this way. So this is the energy, the resolution on energy deposited in the substrate. This is the intrinsic energy resolution of your resonator. Okay, battery's done. So, and then do a stick or something. So then this is eta phonon. This is our phonon collection efficiency. This prototype device had 20 aluminum resonators on a 1 gram silicon substrate. And in this, in the Dave Moore's thesis, we measured measured a energy resolution of energy deposited in the substrate of about 380 MeV, which 2012 is definitely nothing to turn your nose up at. Photon collection efficiency of about 7 or 8%, and an intrinsic energy resolution for the resonators of about 6 MeV, with a sub-millimeter position reconstruction in the XY plane, the plane of the device here. And so these are going to be our baseline numbers to compare what we measured in NEXUS. So going forward from this prototype design, there were kind of two goals for developing the detector. One is optimizing the energy resolution. So can we keep a large photon collection efficiency with a single resonator? And what are the main drivers of our intrinsic energy resolution? And for this, we use this small detector architecture. So this is a 2 by 2 centimeter substrate. Additionally, you're interested in, I should say this is, I'm still working with the Caltech group. So these are the goals from the Caltech Kinetic Inductance group, which I joined by proxy when I joined the Fermilab. So the other device architecture is this large device. I believe there's 80 resonators on this 4-inch wafer. And the goal for this is to push up the multiplexing abilities as well as how well we can resolve position. So for this talk, I'll focus on the small architecture here. Questions? All right, works on. Great, thank you. Yep. Perfect. So I'll talk about the energy calibration that we did at NEXUS. And NEXUS is the Northwestern Experimental Underground Site. It is a low background testbed for cryogenic dark matter experiments and superconducting qubits. It is located 100 meters underground in the Minos Hall at Fermilab. This is the hall at which through which they shoot neutrinos to Minnesota. A top-down view, we have a clean room. This is the new one, or the neutrinos come kind of this way. And we have a clean room underground with a dilution refrigerator as well as a lead shield. So we have this cryo concept dilution refrigerator. The mixing chamber stage is here. Below that, we have an internal lead shield that is thermally coupled to the 100 millikelvin stage, I believe. Below that, we have the radio frequency payload plate and the DC payload top hat. And so the qubits and the KIPM detectors live on this RF plate. Our rock overburden at NEXUS gives us a 225 meters water equivalent shielding. We additionally have this movable lead shield, so we can bring, there's another lead shield behind this wall, or lead bricks behind this wall. So we can bring the shield in, and between the shield and this internal lead plug, we get 4 pi coverage for our detector payloads from the shielding. Additionally, we have some magnetic shielding externally and at the 4 Kelvin stage fridge. Excuse me. We have optical photon calibration systems, and we are now commissioning our deuterium-deuterium fusion neutron generator so that we can do nuclear recoil calibrations in a low background environment and a cryogenic low background environment. All right, so the device that we used for this study was the so-called Fermilab 1 device. This is the device. This is a mask of the device. It features a central resonator with an aluminum inductor. Everything else on this device is niobium. These niobium resonators were put there for a different measurement. And so they constitute dead metal on this device, meaning that we don't see any signal from our phonons in these devices. One is that they have a 10 times higher critical temperature. So the delta, the binding energy of their Cooper pairs is also a factor of roughly 10 higher. And they have a lower kinetic inductance fraction. So we do not see phonon signals in this, but they do degrade the photon collection efficiency by absorbing photons from the substrate. Additionally, we have this coplanar waveguide that also is dead metal. There's no ground plane on this, so that we can, other than this aforementioned dead metal, that we maximize our signal collection. And this, I should point out, was fabricated by Osman Wen at Caltech, who recently defended his thesis successfully. And I believe he is off to Panofsky Fellowship at SLAC. So let's see, here's our device in NEXUS. This is looking up at the bottom of the RF payload. Here is the device. Here's our RF connections to read it out. And here is an optical fiber that we use to do our optical photon calibration. We point the optical fiber at the rear of the chip. So all of the superconductors face away from the tip of this fiber. It is a very inefficient process for light to reflect around and become incident on this aluminum inductor. And so we are looking at purely events in the substrate. If anyone's curious, we use this X300 USRP to do our time streams. And we use that to trigger our LED for the optical calibration system so that we have synchronized timing between our pulse arrival times and our readout time streams. We also use this to, while we're reading out on resonance, we also read off resonance on either side of the frequency notch so that we can look for correlated noise between on and off resonance and use those extra tones to clean that correlated noise away. Here's what the device looks like in frequency space. You can see our 10 niobium resonators, our aluminum resonators, this smaller one right here, and then this rather low Q box mode we've seen in all of our devices with the same enclosure. Zooming in on the aluminum resonance here. So the resonant frequency is at the dip of this notch. Looking at it in complex S21 again, the resonant frequency is opposed to where you stop seeing where's the gap. You can then so the fluctuation. So if I'm measuring on resonance here, the noise can fluctuate kind of around the circle. This is the frequency direction, or it can fluctuate in the radial direction. And again, that's that dissipation direction. And so when you have a pulse, you get some shift in both the frequency direction and the dissipation direction. You get about a 3 times larger response in the frequency direction than the dissipation direction. But we can look at those fluctuations in both quadratures and look at the power spectral density of those things. That's what I'm showing here. In the dissipation direction, you see about 3 times higher noise level versus the frequency direction. But what's interesting here is that we start to see some TLS noise. So if you look at the what's this, pink to purple, there's some slight tilt at low frequencies compared to the dissipation noise where it is still white noise. And then as we push higher in readout power, so how many photons we're dumping into the resonator, we start to see this noise prop up in both quadratures that we suspect to be coming from our readout electronics. From these PSDs of noise, you can estimate what your energy resolution would be given some signal template. And so we, as I'll get to, we took some LED data, and from that we developed a pulse template and estimated our frequency resolution, frequency direction resolution on the fluctuations in quasiparticle density to be half a quasiparticle per cubic micron. So it sounds low, but we have our volume of our inductor is 2 times 10 to the 4 cubic microns. So we're still talking about resolution at the hundreds of quasiparticles level. Okay, so we did this LED energy calibration, which I will outline the recipe for before going into the data here. We pulse our LED onto the device with fixed voltage, and then we can sweep that voltage to change the optical power that's delivered. But for a particular setting, we expect a monoenergetic peak in our energy spectrum. The width of that peak is set by 2 components. One is the intrinsic device noise, the sensor noise. This is the 0 energy resolution, if you will. As well as a contribution from the photon shock noise, which is proportional to the average number of photons that are delivered with each pulse. Without going too much into the details, this allows us to measure both the energy resolution and the phonon collection efficiency at the same time. Both the energy resolution as deposited in the substrate and the resolution on energy absorbed by our sensor. And this eta phonon we're defining to be just the ratio of the total energy absorbed by to the total energy deposited. So what we do for each LED setting at some optical power, we acquire some noise time streams and some pulse time streams. We do our correlated noise removal with those off resonant tones, so that brings our noise level down a bit. This is, you can see, quite far from white noise. We are running at these high high RF readout powers, and that was necessary to resolve the photon shock noise. At lower RF powers, the overall noise is too high to resolve. All right, so we do the correlated noise removal. Then we look at all of the pulse windows from our pulse time stream, and we do some quality cuts to remove windows where there is spurious baseline noise or pulses that are not associated with an LED pulse. We then run an optimal filter-based pulse amplitude estimation in the frequency domain on each pulse window. And in this case, we're using, again, the average pulse as our signal template, not some analytical form. So we measure directly what our pulse shapes are and use those as our signal template. For each window, then, that looks something like this. This is for a very large LED voltage. We extract the pulse height, and we create distributions of those for each LED setting. Fit that to a Gaussian to extract the mean and width, and fit it to this 2-component model, where the mu here is the mean value of your distribution for any given LED setting, and this R is the responsivity in whatever readout units you're doing this analysis in. We use this DF over F. So this is not our data. This is just showing from a relatively recent paper. This is an established method. You can see that as they turned up the LED, you get a broadening of these peaks that follows the square root. And so they plotted it as sigma instead of the variance, but either way. All right, so I briefly just mentioned this before about eta phonon. It is not exactly the phonon collection efficiency, but really the end-to-end efficiency of collecting energy from the substrate into our superconductor. There is some fraction of these phonons that down convert to below the aluminum gap, and without putting too much of a error bar on this, you're looking at something like 40% down convert below aluminum. So now onto our calibration. We finally got this paper through the review process like 2 days ago. And so if you're interested in the details, I'll point you to this paper. So here is the data in the time domain, the frequency shift as a function of time for various LED settings. And from this, as mentioned before, you can convert this into how much the density of quasiparticles must change to give you this shift in resonant frequency. And that's what's shown here. So we are sensitive to, these are single digit shifts in density that we're getting from the, in quasiparticle density from the different LED settings. And we see relatively long pulse lifetimes in this at the millisecond level. And should be time to talk about this in a minute or two. What you'll see on a couple slides is a normalized pulse amplitude, which is just taking the maximum pulse amplitude for our largest LED setting and defining that to be 1. This helps the analysis in subtle ways that aren't worth going into. But then we convert that into the frequency domain so that we can do our optimal filtering. So this is what our pulse shape looks like in the frequency domain for, again, that same series of LED voltages going from the largest signal to the smallest signal. And the optimal filter compares this pulse template and an average noise PSD to the frequency the power spectral density of each individual pulse window. And from that, you can extract what the optimal estimation for the pulse amplitude is. We took noise. So what I haven't mentioned is that we take a long time stream for each window here, 200 milliseconds, then we cut it in half, and we use the second half to characterize the noise. We use the first half as our signal region. And that's where you get these noise PSDs for the different voltages. Then we take also dedicated noise runs to make sure we're not seeing anything different. The dashed line here is the mean of all of these things, and that lines up with the dedicated noise run. There's some fluctuation in the low frequency PSD, but this is a negligible effect once you factor this into the optimal filtering. It doesn't, the uncertainty that you get from choosing a different noise template is an order of magnitude smaller than the uncertainties that we get elsewhere. So once we have extracted the pulse amplitude for each window in each LED setting, we construct these distributions. We could we extract the width and the mean of each of these things. And we plot the variance versus the mean, and we see it follows this line as we expect. From this, we can then extract the fit parameters sigma naught and R. Excuse me. And so from this fit, we determine that our resolution on the quasi-particle density fluctuations as measured by the frequency direction is about half a cubic micron, half a quasi-particle per cubic micron, which is well in line with what we estimated ahead of time. This is just slightly better. And then you can convert that using the volume of your inductor and the superconducting gap to a resolution on energy absorbed by the resonator. And we're at the 2 EV level. Yes.
So the resolution get worse for larger photos. Is it because of photon shock noise or something?
Yeah.
Okay.
Yes, exactly. So if we, right here. So actually, let's go back to this. Yeah. So this is fixed. It's this property of the resonator that you're measuring. And this, if you're broadening the LED, like if you're delivering more optical power with your LED pulse, you're delivering a larger average number of photon, and then your sun width is just the mean variance. Great, okay. All right, so we've got a pretty decent resolution on energy absorbed by the superconductor. It's about a factor of 3 better than the prototype device. However, we also can measure from these fit parameters what the resolution on energy deposited in the substrate is. And this is roughly the same value as was measured in the prototype device, which means we have a very poor phonon collection efficiency of sub 1%. And so just to compare to more modern detectors, we are doing better in the resolution on our energy absorbed by the superconductor. So the intrinsic device energy, we're doing a bit better than the competition. However, we are not competitive in the phonon collection efficiency. So I'm going to come back to talking about phonon collection efficiency in a bit. But first, I'm going to talk about something different. So if there are any questions on that. Okay. So as an aside, I briefly mentioned the quasi-particle generation recombination noise. This is some fundamental limit to the kinetic inductance detector sensitivity. And you can determine if you are able to resolve GR noise in your power spectral densities, you are able to then measure the quasi-particle lifetime. And what we'll see in a minute or two is that quasi-particle lifetime is one of the contributors to your pulse lifetime, and you want longer pulse lifetimes to get better resolution. I'll go into a little bit more detail in that in a second. But you can only do this from your PSDs if you're dominated by quasi-particle number fluctuations and not other sources of noise, either your amplifier or TLS noise. So this is not the case for us. We are not dominated by generation recombination noise. In fact, we don't see this roll off. Excuse me. But we do have LED pulse data at various temperatures. And so from that, we can try to measure the quasi-particle lifetime to get a handle on how our detector is behaving. And so we took a temperature sweep of our fridge and did this LED calibration at each temperature. We did it at a slightly lower readout power to lower this kappa 1, kappa 2 noise that I showed in the PSDs before, because in this case, we're not necessarily interested in resolving the photon shot noise. But we do see there's a strong dependence on the pulse shape. This is just renormalized here, so that they're all have a maximum amplitude of this one. So we are, because of this strong dependence in temperature, we were assured or felt better that we were seeing effects from the quasi-particle lifetime. And as I mentioned, longer pulse lifetimes are good. This allows you in the construction of your optimal filter to sum over fewer frequency components. So you're looking at the low frequency, you can sum over fewer bins if you have a higher signal in the lower frequency bins. So longer pulse lifetimes mean you can get to lower frequencies. And so if you have white noise, your resolution scales like the inverse square root of your lifetime. And even in the case of TLS noise, this f to the -1/2, your resolution still improves, but you're another factor of the square root degraded. And so this trend kind of continues up to the point where you have 1/f noise, and beyond 1/f noise, you don't gain by going to longer pulse lifetime. So ideally, you want white noise so that you can get, and long pulses so that you can maximize your resolution. Okay, so to fit these pulses that we observed at each temperature, we used this two-component fit model that Dave introduced in his thesis. You have a delayed component and a prompt component. With each some amplitude, some rise time, and some fall time. And a priori, we ascribe the phonon lifetime to be the delayed component and the prompt component to be the quasi-particle lifetime. This is the same prescription in Dave's thesis. I should point out that while I'm showing a zoom in here, these fits do go out to longer times. And let's see, the same model we use to fit all temperatures. So from that, we can extract the full times of our pulses. And we find that well, number one, I should say that there are relatively large temperature uncertainties that are shown in this plot. And this is because at the time, we did not have a well-calibrated thermometer on the RF payload. And so we later, in subsequent runs, installed a thermometer that was calibrated so that we could construct a map from mixing chamber temperature to the RF payload temperature. However, and so these error bars are large, which makes making a quantitative comparison of theory difficult. But we can look at kind of this qualitative shape here in a second. So we see that the delayed component extends up to 6 or so milliseconds. And this was the first observation of millisecond pulse lifetimes in our devices. So this chip that we tested here had some sister devices tested at Caltech, and they were never able to achieve pulse lifetimes beyond 100 microseconds. And we believe this to be due in part to some combination of our better infrared radiation shielding on our coax lines going into the device. We have a significantly improved radiation shielding condition compared to the Caltech refrigerator, and we're able to get to a lower base temperature. So all of these things combined give us these long pulse lifetimes. Right, and so as I mentioned, we see that there's a prompt component that we had initially ascribed to the quasi-particle lifetime, and a delayed component that we initially ascribed to the phonon lifetime. But when we saw the results of this, I should also point out the single exponential is because the fit at this temperature was very degenerate between the prompt and the delayed component, hence the large error bars on the prompt fall time constant. So we instead also fit that one to a single exponential, and that was the fall time that we got from this. So if you start to look at this, you kind of see this shape here, and maybe a shape that looks like this. I'll draw some curves there. And so after looking at this, we came up with, or changed a hypothesis to maybe these prompt and delayed fall times actually are swapping their role between phonon and quasi-particle lifetimes around this 100 millikelvin point. And so you have the sum component with a slight temperature dependence that might be expected for a phonon lifetime, and something with a very strong temperature dependence that you might expect from a quasi-particle lifetime. And this general shape has been seen before in measuring quasi-particle lifetimes from pulse, where you get a saturation at low temperatures and a deviation from theory where your pulse lifetimes are a bit longer and also kind of saturate out when you measure quasi-particle lifetime from pulses versus from your noise PSTs. And these are not, again, because of this poor temperature instrumentation, we are not comparing this directly to theory, and these are not theory curves. These are just analytical functions to help guide you. All right, so we ascribe the phonon lifetime to be this component A that follows the slight temperature dependence, and the quasi-particle lifetime to the component B, which has the steep temperature dependence. In that hypothesis, then we're seeing quasi-particle lifetimes up to 6.5 milliseconds, which you can convert then into a quiescent quasi-particle density, which is below 20 quasi-particles per cubic micron in our quiescent state. So this is pretty low as far as we could tell. This is one of the lowest that has been measured for these types of devices. So this is very interesting, but we want to look deeper into this model. And one of the ways we're doing that, I'm going to start skipping ahead because I'm low on time. One of the ways that we're doing that is by simulation. So, okay, so one of our simulation goals here, this is some work by one of my undergraduate students on measuring in simulation the phonon collection efficiencies so we can optimize our designs to maximize that our signal collection. We're still turning knobs and optimizing our G4CMP, so J-on-4 condensed matter physics simulations. But one of the things that we've been working on, myself and Ryan Linehan, who's another postdoc at Fermilab, have developed a simulation, this cap to a simulation chain. It simulates a sensor response, we call it quantum device response. Right now it works for both these KIPM detectors as well as superconducting qubits in a energy relaxation scheme. And so this allows us to take the output of our G4CMP simulation and pipe it into our simulation, which you can input realistic noise BSDs, as well as some other nice features to generate realistic waveforms. This, for instance, is a waveform generated with this tool for 1 keV deposited in the substrate on a 12 qubit chip. How many qubit errors are you seeing versus time? So this is something that we've been using in our group to help us move towards a superconducting qubit-based detector. But one of the things that we can use this tool for is understanding this pulse shape model. We can insert a quasi-particle lifetime into our simulation, and we can control the phonon time profile. So we can generate realistic noisy waveforms like these are data, these are not from the simulation. But we can then run this simulation, do our same analysis on it, and see if we are extracting the correct, ascribing the correct parameters to the correct physical meanings. And so this is what we're working on with this quantum device response. And let's see that. Minutes. I will briefly state where we're going with these KIPM detectors, right? So we have a leading energy resolution for these phonon-mediated kinetic inductance detectors of about 2 eV, but a very low phonon collection efficiency. If we can just push our phonon collection efficiency up to about 10%, which should be relatively easily achievable by removing dead metal, addressing how we're mounting the device, we should be able to get up to a energy resolution or a resolution on energy deposited in the substrate of 21 eV, which would surpass the current state of the art for these phonon-mediated detectors. But if we want to go farther than that, other than continuing to push on eta phonon, we have to improve our intrinsic energy resolution. And so one of the ways we can do this is by reducing TLS noise from the oxide layers that are present in the devices during fabrication. However, we at one point we thought maybe we can go to materials that are known to exhibit less TLS populations in their oxides. But we have seen in all of the materials that we've tested for our devices, aluminum, niobium, and tinitride, we have seen TLS noise. So if we can't mitigate the TLS noise, perhaps we can get away from it. And so we could go to the dissipation quadrature where you don't have TLS noise and your noise is white up to this electronics noise that we had that I mentioned. However, you get a factor of 3 higher noise, so roughly a factor of 3 worse energy resolution. But some work out of Caltech on the large device, they were able to measure the resolution on energy absorbed by each resonator on that 80 resonator device as a function of this parameter, which is kind of arcane, but is related to the RF transmission of your device. And so if you project this out to what would be an optimal value of this parameter, for the dissipation direction in this blue line, you could get to a resolution on energy absorbed by a superconductor of about 600 millielectron volts. But to go further than that, you would need something like a parametric amplifier, something like a kinetic inductance traveling wave parametric amplifier that should give us something to, on the scale of 5, factor 5 improvement in our energy resolution. So just to put that on a plot, because I'd be remiss to not show some projections in a dark matter talk. Here's where we are right now. Here's where we might be in our next device with about 10%. This device is currently under test at Fermilab. So this is a projection for 10%. We're still TLS limited, but if we move to the dissipation direction and make our optimal RF configuration, we can start to push our energy threshold down to the double-digit EVs. If we can then apply a parametric amplification, we can get this down to single-digit EV thresholds. And if we are able to go to a lower TC material like aluminum manganese, we could get down to the single EV threshold. And so that's shown here for a gram-month exposure, background free, for these devices looking for electron recoil in dark matter with a light mediator and electron recoil in dark matter with a heavy mediator. So if we are able to get to this red line here, we start to throw a large region of this freeze-in parameter space. And we think that we have a clear trajectory on how to achieve this. Definitely don't have time to talk about the parametric amplification. In fact, I probably don't have time to talk about this, so we'll just skip all this. I'm happy to talk about, so let me just give you some context here. One of the things that we're interested in is this low energy axis that we see in cryogenic dark matter detectors. We see this exponentially rising low energy spectrum. We know it is not ionizing, so this is a phonon signal. It's been observed in cryogenic phonon detectors as well as superconducting qubits. And so identifying and mitigating this background is going to be critical if we want to actually achieve those lines. So we have not seen this in our KIPM devices yet, but as we push our energy resolution lower and our thresholds lower, this will undoubtedly crop up as it has in every other cryogenic device. So one of the things that we're thinking about for mitigating this are embedded silicon nitride optical strain sensors that you can put basically in your chip and deposit on either on top of the device or on the other side of your chip. And these things will respond to stress buildup in the substrate. Basically, it works in the same way as it's a resonator. So you probe it instead of with radio frequency photons, you probe it with infrared photons. So this is something that I started at Fermilab through the Quantum Science Center. I'm happy to talk about this, but I don't want to go too far over. And as I mentioned before, one of the interests of our group is building a dark matter detector, a low threshold detector built from qubits. And the reason for that is because much to the chagrin of the quantum computing realm, qubits are very sensitive and they don't take a lot of energy to destroy their state. So perhaps that would be a good detector medium because it only takes a small amount of energy to disturb that and we can reliably read that out. And so one of the things that we are pursuing is how do we go from quantum computing style chips into quantum sensing style qubits. And so that's the forward of this problem. But because we're all high energy physicists and have experience with cryogenic particle detectors, as well as backgrounds and general superconducting readout thing, we can we can bring our expertise from our group back to the quantum computing side of things. And so there are a number of things that are relevant for dark matter direct detection. There are a number of things that are relevant for quantum computing. There's a number of things that are relevant for both. And so our group is tackling a number of these items here. So just to quickly run through, and then I will wrap up. We talked about energy detection and photon collection efficiency. We talked about some of the simulations that we're working on to understand photon collection efficiency better and understand the position sensitivity of our devices. We're looking into these optical ring resonator strain sensors to help improve or mitigate potentially dark counts or error rate in qubits, investigate quasiparticle poisoning from stress events, and mitigate noise. We've deployed superconducting qubits underground to measure our correlated noise. So basically, if some cosmic ray comes through your qubit chip, it deposits enough energy to wipe out all of the quantum information across the chip. Every qubit gets hit for the most part. And traditional error correction codes can't handle that because they are all these errors are correlated in both time and space. So this is a problem. So we were able to measure the rate of correlated charge noise and so correlated errors in our qubit chip on the ground. And we were able to get, we observed no correlated errors above 3 millimeters on a length scale of 3 millimeters by operating in this heavily shielded environment. There's some interesting results in this paper about potentially an unseen background that could be due to the stress that I had talked about, these stress releases, the low energy excess. We've also developed this cryogenic optical beam steering device that basically allows you to bring in a room temperature light source into your fridge and steer it across your device. We are looking, so this is a paper led by Ryan on, okay, what are the optimal parameters or some of the optimal design choices you can make when you're building a qubit-based detector in some energy relaxation scheme. We're also expanding our simulation capabilities to look at novel materials and bringing these into this JF4 condensed matter package. So these are really pretty pictures, so I had to show them. And we have NEXUS where we did this work. This is largely focused for the dark matter direct detection side of things. And then we have this quiet facility, which is brand new, more or less dedicated to quantum computing and QIS issues. So I think I haven't gone over and even maybe have some time for questions. So I'll just leave the conclusions up here. I just want to say thanks to most of my team here. This is a relatively outdated picture, but we collaborate with closely with Northwestern and Illinois Institute of Technology, as well as some external collaborators. Specifically for this work, the Caltech team is really instrumental. That's all I have. So happy to answer any questions.
Any questions?
I know you skipped, but could you comment a little more on the TLS?
Yeah.
So like, or the context of like if your sensor could be used to characterize TLS in whatever layer they're using.
Yeah, so basically, so if you talk to qubit people and you talk to MKIT people, TLS means something kind of different. In qubits, you're concerned about a TLS that kind of ends up near your qubit frequency and gives you some avoided level crossing that won't allow you to read out your qubit. So they resolve basically individual two-level system sites. We see kind of the ensemble of two-level systems that are present in the oxide layers where there are high electric fields, so in our capacitor. There's some work on the Caltech side of changing the capacitor design, going to a parallel plate style capacitor using amorphous hydrogenated silicon as the dielectric, and that has been shown to have very low TLS population. So that's one way that we could lower our noise and retain the gains that we get by reading out the frequency direction versus the dissipation direction, mitigating that TLS noise, and then getting the quantum limited amplifier would get us, more. It would gain us more than if we just stuck to the dissipation direction. So let's see. Yeah. So I guess your question was about sensing these things. So when you measure the on resonance PSD, this, you'll see some character. So you on resonance, you're measuring the fluctuations in time of your noise, basically. And the TLS has been seen in many devices and has this characteristic 1/f shape. So we characterize it by basically the amplitude in noise power of this component of the noise background or the noise budget that we have. So in the paper that I had shown, we do this decomposition of our noise spectrum. We do a little bit of cleaning using the dissipation direction to clean any correlated noise out of our frequency direction. Then we say we've got some white noise that we take the white noise from a readout power where we're amplifier noise dominated. We scale that by the change in readout, so that the change in readout power. So that's fixed, the amplitude of this thing. We fix a resonator ring down time in this fit, and then we say, okay, so what's our TLS component? And that's this orange line, and we find that our this if we didn't know it was TLS ahead of time, when we measured this and we see, oh, it follows this at the -1/2 dependence, that is the smoking gun of TLS noise. And so that is how we measure it, by basically what is the, take some reference frequency, usually about 1 kilohertz. What is the noise power of your TLS component? And that's basically the lower that is, the better you've done at mitigating TLS. The higher it is, the worse your TLS is. Did that answer your question? Yeah. Okay. Thanks. Yeah.
So if you were to observe one of these, disturbances in that peak, what are the next steps for determining, like, once and for all, whether or not it is a signal, whether or not it is dark matter or some other kind of energetic particle that could create a disturbance like that? Like, is there a profile that, like, a charged particle like a muon would create versus like a neutral dark matter type of particle?
Sure. The answer to the last part of that question is no. So we don't apply so if I find a device picture, we don't apply an electric field to our device, to the device substrate itself. And so any ionizing particle is going to produce ionization. That ionization is going to instantly or quickly recombine and spit out phonons. And so we only see a phonon signal here. And so we don't have necessarily particle ID. As mentioned before, we can discriminate between events that directly hit the superconductor and that originate in the substrate based on their rise times. In order to, okay, so then two parts to this question. One is if you have your dark matter detector, so the paradigm for a dark matter detector is you have your very sensitive dark matter detector in the center, and then you have layers and layers of veto detectors. And so you could imagine something very similar, where you are looking for, building bad dark matter detectors on the outside to pick up backgrounds, and use that to veto events that come from your device and don't hit anything else. Then if you are relying on that, then you're exposing yourself to these low energy excess events that we get an indication that these are coming from stress release events. In order to actually find, the smoking gun of dark matter, you want, a number of things. You want to look for interactions on different targets. So we could consider changing out the substrate or running multiple detectors in parallel with different substrates and seeing if we see compatible signals across all of them that would match what we think about dark matter. If we were able to really push the sensitivity of these things, we could look for things like annual or daily modulation. Those are a bit stretch goal for something this size. But those are all ways that you would want to really nail down and say, yep, this is dark matter. Good question. Yeah.
I'm just curious, what are the pathways to mitigate these low energy excess that apparently people are seeing?
Yeah. So one of the things that I'm going the wrong way.
Is there any glue on the substrate?
No.
This is known to.
This is yes. This is known. So we have no glue on our substrate. Let me show the. So this is not what I was looking for, but there is a paper out. It's the. Doesn't matter. I have a link that I can find for you. Here you go. This one. Basically, if you glue your chip down, you make your stress backgrounds really bad. And if you hang it from wire bonds, you make it better, but you still have stress there. And so one of the things that this paper, let's see, here we go. This paper talks about is that even if you were to have your device somehow magically levitated in a cryogenic environment, you would still get stress relief events because of thermal contraction of your superconductor, thermal contraction of your substrate, and the interface between those things contracting at different rates. And so stress release events in your aluminum can inject phonons into your substrate that then can propagate around and hit other sensors. And so you need some way of building low stress material. I don't think that's a reasonable thing to do. I think you're going to want to stick with aluminum and traditional superconductors that we know about. So instead of trying to get rid of it, what you can do is tag it. And so you can, if you have something that responds to changes in your stress field, then you can use that to veto phonon signals. And so that's what this work was targeting to do. Basically, if you have a stress buildup, so some stress is building up in your detector. Yeah, so in your detector, you've got some stress building up as you're contracting. At some point, that stress is going to relieve and spit phonons out, into your substrate. And if you have some sensor that is inert to these phonons, but is sensitive to stress, you might see something like this. So this is obviously a cartoon. We're still in the early stages of this project, but you could imagine seeing on your optical ring resonator some change in transmission at your resonant frequency, and then an abrupt change when that stress relief changes. And so the way these work is through the stress optical effect. When you compress the dielectric, it changes the index of refraction, and so that changes your resonant frequency. And so you could say, all right, if these things are insensitive to athermal phonons, I see a stress release event. I look in my qubit or I look at my dark matter detector, and if I see a pulse there, I know that it came from these phonons, and I can reject that as a background event. And so there may be no way to mitigate these stress reliefs events as like getting rid of them, but you can at least exclude them from analysis.
For qubits, it wouldn't work because it destroys everything.
Yeah, so qubits is a little bit. So I don't work on the quantum computing side of things, so I'm not really very well versed in error correction schemes. But one of the things that you could maybe think about doing is if you have some kind of hybrid quantum processor and a classical processor, you could, if you can measure this and you built up some distribution of the amplitude of these drops, you could potentially say, I'm measuring a buildup of stress. There's some probability that in the next 20 microseconds or something, we're going to have a stress release event. Let me offload all my quantum information into a classical processor, let that stress relief wipe out all my information, then reload the information and like kind of pause your computation to let that stress go away and then continue. This is not well fleshed out. This is just my non-quantum computing brain thinking about how you might do something like this. Good question. There are some other hands. Yeah.
Is there any particular reason why you use a lumped element type of resonator versus like a distributed CPW resonator? So you don't have those strong electric fields and the detrimental coupling to TLS. Probably higher Q as well.
Yes. So I believe that was in the Caltech group before I started collaborating with them, they were using those, and I don't have a solid explanation for you as to why it was chosen to switch. Maybe Dave knows.
Yeah, I mean, you can have no ground plane, and the TLS noise is actually better in these because you can make the capacitor quite big. So the local electric field is smaller.
Okay, yeah.
Next. Yes.
A lot of TLS noise, one of them had may have been some acoustic peaks or something.
Oh yeah, so this is I know what you're talking about, but this is not. So this is from a review paper. You're talking about this plot here. Yeah, this is from a review paper. So these are So some noise source that couples to the dissipation direction. I don't believe it's actually discussed in the review paper.
It doesn't have to do with the mechanics of the silicon aluminum.
I don't believe so. I think we don't see things like this in our dissipation direction. We see maybe a spike in, if I go back to our PSDs, here you go. So like we have a peak in our, so that's just dependent on your operating conditions. Maybe it's, picking up the PTR vibrations on your fridge, or maybe you have construction happening next to your building and all of your stuff has gone haywire. But nothing fundamental there.
Is it a good microphone?
I don't. We have had vibrational issues in our fridge as measured by the DC payloads. We've never seen the same noise on these detectors, so maybe they're a bad microphone in that sense. They're a little bit more inert to vibrations than the DC detectors that we run, but we haven't done a really in-depth comparison of that.
Right, we're out of time for questions, so let's thank the speaker again.